Okay, so today, this is actually good practice for me. I don't know if it's the best for you guys, but today we're, as usual, doing things in reverse order. So we'll do the advanced topics first, which depend for their full understanding on the main lecture, which comes second. So that's not entirely bad in medias res to sort of start in the middle of the story. So we'll talk about navigators. So navigators, there's a whole bunch of different kinds of these that we'll talk about, and then the different kinds of distortion that you get in EPI and spiral. And like I said, to fully understand this, we'll talk about the two theorems about phase and frequency in Fourier land. So there's the Fourier shift theorem and the Fourier frequency shift theorem. And you could call the first one the Fourier phase shift theorem, and the second one the Fourier frequency shift theorem. So so we'll talk about that in the main lecture, but we'll assume those now. So to start off, so navigators. So what are navigators? They're basically it's kind of a little bit like when we were talking about quantitative T1 or quantitative scanning. In order to do a better job of that, you need to collect more data. And so navigators are basically a tiny bit of data that you collect at the beginning of a scan in order to correct the data that comes in later in the scan. And this could often be just collected in just a couple milliseconds at the beginning of a scan, and then applied immediately to that scan, like even to a slice. And so we'll see like when you do echoplanar imaging, typically there's a navigator for every individual slice. So every 70 millisecond slice, there's going to be a little navigator at the beginning, and the information that you extract from the navigators will then be immediately applied to the rest of that slice. And that really helps out a lot with making your data better. So we'll explain how that works. Now, if you open up a MRI textbook and look at navigators, one of the places where they're often used in the clinic is for breathing. So what happens when you breathe? Well, one of the things that can happen is your diaphragm goes up and down. And so if you're trying to image the lungs, obviously this is going to sort of make a blurry mess of things because it's moving the lungs up and down. So one of the uses for a navigator is to actually kind of figure out where the diaphragm is. The diaphragm is a high contrast feature in the image, and so if you figure out where the diaphragm is, then you can try to do a better job of imaging, especially the lower part of the lungs. That's where the pneumonia tends to build up. And so if you want to actually sort of image that, then you could sort of follow the diaphragm, basically. So that's a typical kind of navigator. But there's two things that we're going to talk about in the case of EPI. So we could say lungs, but what about EPI? Because that's something that we typically use for fMRI. And so every single EPI image that you probably have ever collected had navigators in it. And so what are the navigators? So there's two particular things that the navigators could be used to fix, and one of those things is basically B0 drift. And another thing is sort of gradient balance, left-right gradient balance. So, and both of these things will cause major artifacts. So if you look at the way you normally do echoplanar imaging, is you go to the corner. So here's K-space here. So you do an RF pulse. That puts you in the center of K-space. And then you go to the corner of K-space and start going across. So one of the problems that can happen when you do this, so then we go down here, and then we go across, and then there's a blip, and then we go across this way, and a blip like that. So that's a standard EPI. But one of the problems that can occur is that the B0 might have drifted a little bit. And so how much does the B0 drift? It drifts not very much. So what is drift? So drift just means the B0 field gets slightly less strong. And we said that we have superconducting magnet, which means that there's no resistance, which means that the B0 shouldn't drift at all. But in fact it does. On a very regular basis, because there's various other ways of kind of extracting energy from the magnet. And so it's about 0.05 parts per million per hour. So that's not very much. That's not going to do anything over, it's going to be barely visible over 5 or 10 years. But since we're relying on the B0 to be very exact, that can actually be a problem. And so it's actually enough of a problem that within a 5-minute scan, the B0 will drift down enough to cause an image shift. So how does it cause an image shift? It's because if this is unaccounted for, this will cause a phase shift because the precession will be slightly different than what we were expecting. So this causes, you could think of it as, like I said last time, it's a phase pedestal. So it applies to all of K-space. So basically it slightly disturbs the phase of the signal. So the precession, you're expecting the precession to sort of start at 0 degrees and go around, but instead it's starting at 10 degrees. Now that little difference just in what you consider to be the phase will cause an image shift. So this phase shift, that will be the Fourier phase shift theorem. So this causes an image shift. And this image shift, it's virtually always in the phase encode direction. So, in phase encode direction. And the reason for that is that in the case of in EPI, in the case of EPI, we have these little blips that move us up to the next point in KY. So this is KY and this is KX. And those are very small compared to these very large gradients that are going back and forth. And so if there's a little bit of a error in the B0, it's much bigger relative to the gradient caused effect in the phase encode direction. And so what will happen is the image will shift up, and it'll actually shift up on the order of a pixel or two. There's non-trivial amount of shift during a scan. Now that's not too hard to fix. You could just do a motion correction and put that back. but it's kind of irritating to always have that since we know that the frequency is smoothly drifting down. So that's one problem that we might want to fix with a navigator. But there's another problem. Another problem is the gradient balance. And so what's the gradient balance? So if you collect data, what ought to happen is when you go left and right, so when you go this way across k-space, you ought to get an echo that's centered in k-space. And then when we turn around and go this way in k-space, you ought to get an echo that's also centered in k-space. But if the gradients are ever so slightly asymmetrical, so that basically they're a tiny bit stronger in one direction than another, you can get various pathologies. And so one thing that you could get would be to have alternate lines of k-space shifted. So one thing that can happen is, so if I just draw where the echo is very strong, so you might have something like this where the echo is very strong, but it's a little bit off center like that. So every time you come one way through k-space, it's slightly displaced. So it puts you slightly in the wrong part of k-space. And so if you look at, of course, the one down here is going to be bigger by far than those other ones. But basically, if you have that kind of sort of so-called zipper artifact, what is that going to do? That will cause a very large ghost. So, and one of the homework assignments is to actually simulate that. So what will happen, this is k-space. When you reconstruct that data, what will happen is you'll get basically a ghost that shifted. I'm telling you the answer to the homework problem. You get a ghost that shifted half of the field of view. So here's half of the field of view. So this guy will be shifted up, and so you'll have another copy of the brain that will wrap around like that. And that's called a Nyquist ghost, and the reason for that is that it's a ghost caused by something that's occurring at the highest spatial frequency. So it's a defect that is just between adjacent spatial frequencies. So that's something that we need to correct. In addition to this phase, phase problem because of the B0 drifting and then the spins getting out of phase from what we're expecting. So how is this? How is this done? So back in the day, I always like to say back in the day when we had to walk 10 miles through snow to do our scans. So back in the day at UCSD when we first bought Varian magnets, you just did this completely manually. So what you would do is you would do it with the person in the magnet. So what you would do is you would put the person in the magnet and then collect a scan with the blips turned off. So basically, if you turn off the blips and just go back and forth repeatedly, you'll just get a whole bunch of echoes, and you'll end up with a picture like this. A whole bunch of bright echoes because you're going through the center of k-space repeatedly. They'll get a little lighter as you go down because of T2 decay, but you'll basically have a strip like that. And then we had some settings that were called tweakers. So you just would tweak the tweakers, collect another one until you got rid of that artifact, until you ended up with the left and the right pass all perfectly lined up. Another thing you could do, what if the echoes came back over here, like that? That turns out to be a Fourier frequency shift error. That turns out not to cause too much trouble, but you might want to move those guys over where they're supposed to be, where they're centered. You could even have something else, like what if the echoes are the gradients are slightly imbalanced and the echoes start going down that way? That could be another problem. So how can we solve those problems with an extra scan? And we have to do it quick. We only have like a couple milliseconds to solve this problem. So the way this is done is when you first go to K-space, instead of immediately going down to the corner, just go across K-space a couple times. So go across K-space a couple times, 2 or 3 times. Very quickly, at the beginning of the slice, maybe we could go back again. So what does that look like, in terms of the gradients? Well, normally the way EPI works is you do the slice select, and then you go to the corner of K-space, and then you start, doing your big readout, and then your little blips that. So that's the normal EPI. But what you do instead is basically before you start up this thing, what you do is just go back and forth a couple times. Without turning on the blips. So here, no blips. And then now you can say you're at this point. So this is kind of the now we're at that point. And then you can start turning the blips on. So no blips until you're at this point, and then start turning them on. Start turning them on right here. So it's like a trivial difference in the scan. Usually there's a little bit of a delay because we have to process that data very quickly. Like we only got 1 millisecond to process that data to sort of figure out. So I just kind of jumped ahead. Like, what will you get out of this? Well, what you'll get out of this is 3 big echoes. So you'll basically get, like a big echo going across K-space one way, and then a big echo that might be slightly offset going across K-space the other way, and then a big echo, back to the same way. And so these guys will be, the peak of these guys will be slightly off. And so what you have to do is very quickly find the maximum, maybe find it in a couple, average those two, figure out what the difference is. You want to know what this difference is here, and then figure out how to quickly tweak the gradients to fix that problem. And then immediately apply that fix back to this gradient, so that all the data from then on will be collected with all the echoes from the left and the right direction lined up. So that's one thing you can do. The other thing you can do is just look at the phase. Look at the phase of the echoes after you fix them. So fix the left and right business, and then look at the phase, and then you can use that to stop the drift. That's this B0 drift. So then the image will be in the same place in the phasing code. So strangely, the drift just causes a problem in the. Not strangely, it's just because the blips are so small. It only causes a shift in the B0 direction. So this is now built into scanners in order to essentially give you better, more reliable EPI data. You could have done it manually would have taken another 5 minutes or so, just to sort of actually you just basically look at the raw case-based data, just the raw echoes, and then just try to, manually adjust the gradient tweakers to line them up. But this is an example of a navigator. So it's something that basically is a very very quick and dirty measurement that is then immediately fed back into the scanner in order to collect the rest of the data more reliably. And obviously, one of the things with any kind of scheme like this that you always have to keep in mind is that you've got to be super reliable, because you're actually actively changing the rest of the data collection. And so there's no going back, in a way. You can't say, oh man, I set my tweakers bad and it completely messed up my data, because if you do this calculation here incorrectly, you could possibly make the situation worse. But too late, you've already collected the data in that state. And so one of the things about these hidden engineering things is they have to be very reliable in order to, because you're actually directly affecting all the data that comes in afterwards. So that's one kind of navigator. So let's talk about, and so that's done for every EPI, so every echoplanar slice. For every multiband slice, you would do something like that. And it, like I said, it has the advantage that the slices won't drift from this slow rundown in the magnetic field. So another use for a navigator, which is completely different than this, is to try to use a navigator for motion correction. And so it's kind of similar to what we talked about with the lungs. So that first one was, there, we'll put this up here. So the first one was EPI shift / Nyquist. But you can also use this for motion correction, and that's more like the lung case. So how does this work? So once again, the problem is we've got a problem with doing this really quickly. And so let me just sort of briefly go over the stuff that I talked about on motion correction a couple lectures ago. So for motion correction, obviously, the simplest thing if you're recording a lot of images is to, just do it post hoc, just afterwards. So basically just line up the data, line up each volume as it comes in with the previous one to fix that. That doesn't work for 3D. So if you have a 3D scan, like a 3D echoplanar scan or an MP Rage, you're not collecting the data, and you're not assembling the image until the very end. And so if motion got in there, there's no easy way to fix it because you don't have an image to align yet, because you haven't made the image. So then there was this, what's it called? PACE? I think it's called PACE. Motion correction on the Siemens scanners. And the way that one works was that's a little bit less far behind. So the idea is you collect a volume, at T1, and here's T2. And then at this point right here, align T2 to T1. And then very quickly, adjust gradients. So adjust gradients to cancel. And so then T3 will be correct. So T3 will now be aligned back to T1. Now T2 clearly is screwed up because that one's not corrected, because you couldn't determine what the error was until after you collected it. And so when you're all done, you'll have to run a whole motion correction to fix the guys that were one behind. But then you could just continue doing this. So at this point, do the same thing. Align. So here we aligned 2 to 1, used it to correct 3. Now here we align 3 to 2, use it to correct 4. So, so basically you just repeat like this. And then when you're completely done, then you run an alignment on the whole thing to correct the ones that were used to derive the correction, but obviously couldn't be corrected because you hadn't collected the data yet. So that generally works reasonably well, especially if you don't move a lot. But you can see it's always one behind. One behind. And it doesn't work for 3D. So another plan is, why don't we just try to quickly collect enough data to tell where the brain went to so that we can then fix the collection of the current slice. And so here's an example of how to do this. I have a paper that was originally written probably in 2000 or something. It took a long time to sort of implement this, but basically what they did was something kind of like a spiral. So if you look at, and why that? Because, spiral, because you can do it real quick. And so the idea is you, before you actually collect your real data, so in other words, you have to do this, you only got a couple of milliseconds to do this. So we do an RF pulse, select the whole volume. So get the whole volume. And then do basically a spiral. And what we do is we turn this gradient on continuously. So what does it look like in K-space? So in K-space, what we're trying to do is collect a sphere of K-space. So here's the 3 dimensions of K-space. And so what we're trying to do is basically collect a sphere like that of K-space, all at one spatial frequency, one relatively high spatial frequency. So spiral navigator, spiral nav, collect sphere surface in K-space. That's one spatial frequency. It will be one spatial frequency. So what is it actually? You're stamping on, say, 20 stripes onto the, or 50 stripes onto the entire volume, and then you're just sampling all the different possible orientations of those stripes. That's what a sphere in K-space means. So, and why is this gradient on continuously? Well, that's just sort of to move you. Say we started at the bottom. It's just to move you up the sphere. Slowly move you up the sphere. And then what causes you to go around the sphere? That would be the spiral gradient. So while that's on, you've got, you might say, go to the bottom of K space, and then do a spiral, and then maybe a crusher to get rid of any extra data, because we're about to collect, real data collection here. So here's the other spiral gradient, and maybe another crusher. So basically this is, and then we just collect a whole sphere of K space. We haven't said why we want to do that yet. I'm getting to that. So how does this work? So this works by taking advantage of the following. If you rotate an object, if you rotate object, it turns out that rotates K space data. So that's sort of interesting. So a rotation actually just physically rotates the K-space data around. So you can see this in MATLAB. You can just take K-space data, rotate it. You got to figure out how to rotate all the data. That's a little tricky. But if you do that and then do the reconstruction, you'll see that will just rotate the image. So nothing fancy there. A rotation in real space equals a rotation in spatial frequency space. That sort of makes sense because you're just kind of rotating the stripe patterns. But we also need to know the translation. So the translation, translate object, there's three different directions, X, Y, Z, that we can actually move the object. So what does the translate the object do? The translate the object is the Fourier shift theorem in the main lecture today. And that just causes a phase shift. Phase shift in K-space. So a phase shift causes a translation. A translation causes a phase shift. A rotation of the object just causes a rotation of the data in K-space. So if we look at the data that we get, what we're going to have is we'll have a sphere of data, and what will it look like? Well, like I say, it just looks like some clouds. We'll just have some little smidgen-y stuff like that, sort of going around K-space on that sphere. And so say there's and it just represents whatever spatial frequency we picked in the brain, but it should be the same. And so then we can look at another one for the next. We can essentially just collect some data for the first scan, figure out, where the little clouds are, and then what we can do is, collect, say this is, time t equals 1, and now we get t equals 2, and then we say, oh, actually I can see that basically we've, rotated this guy a little bit. That guy needs to be rotated. There'll be different angles to rotate, but we can very quickly, we only got 5 milliseconds, 2 milliseconds, line up this second K-space data with the first K-space data. And that tells you the rotation, and then look at the phase. So look at the phase of that data. So this is just lining up the amplitude. So we can sort of, align amplitude. And, by rotating, and then calculate translation from phase difference. So if we calculate translation from the phase difference, we can actually, it's a three-dimensional sphere, and so we'll have information about how the phase changed in x, y, and z. And so we can calculate the x, y, and z offset. And so then, at that point, we haven't collected the data yet. So here's the real data collection. So we haven't collected the data yet, so all that computation goes in here. Computation. So we do our computation in there, and then quickly fix the gradients to cancel out that motion, and then collect our real data. And then our real data will be lined up. So this is an example of how to collect some additional data very quickly to try to fix the main data collection and get rid of the motion. Now, what's the advantage of that? Well, it's especially good for a 3D scan, because this will work with a 3D scan. 3D OK. Because it doesn't rely on constructing an image. And so you could do this during collection of a 3D scan, and even though you weren't reconstructing an image, you could still do this correction and end up, so if you had an MP rage, for instance, it's particularly good for something like an MP rage, because with an MP rage, there's kind of a gap. There's a natural gap. Because you do an inversion, and then you wait a while, then you start collecting data. So there's this gap here where you're waiting for the recovery. And that's a perfect time to do something like this, because you're just waiting around. So so it's particularly good for something like an MP rage where you have to wait. But you could also use it for an echoplanar imaging, where you could just collect this very quick and dirty data to try to sort of correct for motion, just measure the motion. Now, one thing is it interferes with this, you've got to add something to the scan. And so another, option for motion correction that I mentioned last time was you could use a camera. And so the camera is just collecting data on the head, where the position of the head is, and then using it to feed back in. That doesn't interfere with the scan. It doesn't interfere with the pulse sequence. And so, but of course, then you've got to have a camera set up. You have to have a marker. So basically the camera is looking at the marker in stereo. So it's using two different cameras to look at a marker and figure out where the position of the marker is, and then feed that information back in to the scanner to cancel the motion. Okay, so that was the sort of navigators, sort of a quick summary of navigators. There's something that was written at UCSD called Promo that does something very similar to this, where it for correcting an MP rage, doing motion correction in an MP rage scan. That was written by Nate White. So I have that. I'm pretty sure I have that reading if you want to see in detail how that works. So you can see motion is a problem, serious problem. That's why I like to sometimes scan dead things. You can scan them for 24 hours. And as long as you got it battened down, it's not going anywhere. So okay, so now I want to talk just quickly about the kind of spatial distortion that you get in an EPI scan versus a spiral scan, because I mentioned that last time, but I'll just try to go over it in a little more detail, and then hopefully when we talk about the main class, I'll explain it more slowly. So the problem with an EPI scan is that it's actually collected over time. So you go like this back and forth, etc. And what does that do? That gives time for more error to accumulate on the later parts of k-space, more phase error. So what's going to happen is there'll be a lot of error up here, and a little bit less down here, and a little bit less down here, a little bit less down here, like that. So the error across k-space is not constant. So that's a problem. So what does that actually do to the image? So it's a little complicated. So let's just take a case of an image that's say just a line. So this is k-space. So here we'll draw the actual image over here. So the image, say the image was just a line like that. Okay, so this is our, because an line is kind of easy to deal with. Here's our image, just a line. And now let's assume there's something, the thing that's causing the error. So now we have to sort of like assume what's causing the B0 from, this is from B0 problem. So what is the B0 problem that's causing the error? Let's assume that the B0 problem is a spurious X gradient. So B0 problem is spurious X gradient. So it's a spurious X gradient. And so what does that mean? Well, this is the image. So this is the X direction in the image and the Y direction. So this is the here this is kx going that way and ky. So there's an X gradient, and so what does that mean? That means the gradient's going in this direction, and it's a spurious X gradient. And where could that come from? Well, an example is that we haven't talked about this either yet, but you want to do shimming to try to flatten the B0. And what are the things you can use for shimming? One of the things you can use is the gradient. And so say our shim calculation went a little bit bad. If our shim calculation went a little bit bad, and we put a gradient on that we shouldn't have, or we turned a gradient off that we shouldn't have. There should have been a little gradient to flatten the field. And because for whatever reason the person has like a head that's bigger on the right side, and it needs a little bit of a gradient to keep the B0 completely flat. So this is our problem. So this is a line plus a spurious gradient. So what does that do? Well, what that's going to do in space, is it's going to essentially cause a phase error, that is bigger and bigger when you move away from the center of real space. So this is, don't forget, so this is, image and k-space. And so what is that going to do when you actually reconstruct the image? So when you reconstruct the image, what you're going to get instead of a line So this is, x and y, not, so here's ft minus 1. So when you reconstruct the image, what's going to happen is you will just shift, you will shear this little bar. And so this, what you'll get is a shear. And what do we mean by that? It means something like it would transform a square into a rhombus. So it's a non-rigid transformation. It will sort of it will deform the object in a linear way. It's a linear transformation, but it's non-rigid. So some linear transformations are rigid, other ones are non-rigid. There's no bending occurring, it's just shearing. So you just took the square and just like scrunched it up like that in the vertical direction. So that's what it's doing to this line, actually. This line is actually, it's like a little rhombus. Now, that can be corrected. There's various ways of correcting that, like collecting B0 data. But it's sheared, but sharp. So, sheared but not blurred. So it doesn't, so that's the thing about this is, but not blurred. And because of that, people have tended to prefer this kind of scan to a spiral. So this this whole thing on this side is the EPI, where we collect the data sort of non-uniformly with very large gradients in the kx direction and much smaller blips in the ky direction. That's why essentially this thing only moves in the y direction, doesn't move in the x direction. So all the actual movements in space are just in the phase encode direction. So these are sheared in phase encode direction. In phase encode direction only, but not blurred as a result of this spurious gradient. And this is very common kind of distortion you actually have in your images. It's a little hard to see because it doesn't, you just look at the brain, it looks sharp, but you don't realize it's actually just slightly like that. And the thing is, brains actually in real life, when you compare them to each other, some people's brains look a little other ones look a little so you can't even see it for the most part, but it's there. But because it looks sharp, people tend to prefer this. So what happens with a spiral? So if you look at a spiral, what happens with a spiral is that here's the k-space of a spiral. If we start at, say we start from the middle, what happens is, and go around like that, what happens is the error starts to build up, and so higher spatial frequencies have more error, or vice versa. If we started from higher spatial frequencies, then lower spatial frequencies would have more error. So this is spiral k-space, and so what does that do if we had a line? So here's our image plus spurious x gradient. So in that case, what will happen is it will cause the higher spatial frequencies to be misaligned with the lower spatial frequencies. And what you'll get instead, when you reconstruct this, is you'll get a line that's kind of blurred. It'll be blurred more toward the, look something like that. It'll be a little blurry. It won't be as distorted. It won't be like sheared in the same way, but because it's more blurry, so not sheared, but blurred. And because of that, people have tended to dislike it, sort of unfairly in my mind, because I would almost prefer something that wasn't quite as distorted but blurry over something that was sharp but incorrect. But people have tended to sort of prefer the EPI distortions, sharp distortions, not blurred but distorted compared to blurred but not as distorted. Now, one thing to keep in mind, both of these can be corrected. So it's possible to correct this kind of distortion if you just measure a field map and then feed that back in, and then essentially correct things based on where the spurious field was. So a field map would pick this up. It would pick up the spurious gradient. It would say, yeah, the B0 is a little bit higher on this side of the image than this side of the image, and so you need to shift things to correct that. Like you could just essentially just shift this, back into a square using, a B0 map. You could do the same thing for here. So it's a little more complicated because what happens is the error is building up. We have to go back into K-space and fiddle with the K-space data to correct the error that occurred as a result of this gradient in K-space. But conceptually, it's a very similar thing. But people have rarely set that up to do it. That's again, that's kind of like a task for the future to make to sort of automatically collect a B0 scan when you're doing a spiral, and then use it to correct the spiral data to make the spiral data sharp again, because that would sort of correct the blur in the spiral data. So the bottom line is that when you're doing these scans that take a long time to collect the data, you'll get different kinds of distortions depending on what order you collect the data in. So you'll get sort of this typical shearing or shifting motions in the phase encode direction, because this shearing is always going to be in the. Okay, we will end right there. Okay, so questions about sort of navigators or the EPI versus spiral?